In this tutorial, we'll be looking at pH of strong bases and how to go about questions that involve very diluted strong bases. Okay. Now, strong bases, just as a quick reminder, we mentioned that strong bases are usually hydroxides of group 1 metals. So we can say that lithium hydroxide is an example of a strong base. We can say sodium hydroxide is an example of a strong base. You can say cesium hydroxide is an example of strong base. So hydroxides of group 1 and in group 2, we can talk about beryllium hydroxide all the way down to barium hydroxide. These are some examples of very strong bases. Okay, and how do you calculate the pH of these strong bases? How do you calculate pH of these strong bases? Now, let's consider let's consider 0.1. Sorry, so this is 0.1 molar sodium hydroxide, NaOH, aqueous, of course. Now, how do you go about finding the pH of this solution? Now, we have sodium in aqueous solution because it's a strong base. It will prefer to stay at electrolytes. So, sodium hydroxide as an electrolyte is going to give us, is going to dissociate, and we will have sodium plus OH minus, and this is aqueous. So initially we're going to be having 0.1 molar sodium hydroxide. At that time, we won't be having any sodium plus in solution or OH minus. So we say 0.00 initially. Then the final concentration after everything is associated is going to be 0.0 for sodium hydroxide because we are not going to have any of that in solution, but the ions. So sodium plus in aqueous solution is going to be 0.1 and OH minus will also be 0.1. That means everything dissociated. So from this equation, we can say that OH minus concentration is equal to what we have here, which is 0.1 molar, 0.1 molar. But then we know that POH is equal to the negative log of OH minus concentration. And so when we put that into the equation, we're going to be having negative log of 0.1. That is the concentration of hydroxide anion. And so this will give us a POH of 1, right? So one thing we have to know is that when the pH is very small, that means it's a very strong base. Okay, it will give us a high pH. So from this particular one, we can find pH. We know that pH is equal to 14 minus POH because pH plus POH gives us 14. All right. So when we subtract that, we'll have 14 minus 1, which is equal to 13. So the pH of sodium hydroxide of 0.1 sodium hydroxide is 13. Good. Now, what about the same concentration for magnesium hydroxide? Magnesium hydroxide is MgOH2. Okay. So this is aqueous. Now, when this dissociates, it will give us magnesium 2 plus OH minus 2 moles because we have 2 here. So this also is aqueous, right? This is also aqueous. So what happens? Initially, the concentration here is 0.1. Then after everything dissociates, know that this will dissociate completely because it's a strong base. So initially, we're not going to have any ion in solution. Then finally, everything will dissociate and then we'll have 0.1. But OH minus, the mole ratio is 2 is to 1. So the amount of OH minus we're going to be having in the solution is going to be twice the concentration of magnesium hydroxide because the mole ratio is 2 is to 1. So we'll have twice 0.1. Okay. So if you look at this, we find out that the concentration of OH minus, which we are interested in, is 2 times zero point 0.1, which is equal to zero point 0.2 molar. So again, POH is equal to negative log of OH minus. So we put that in there, minus log of zero point 0.2, and then we're going to be having the POH to be equal to 0.699, right? So what is a pH? It's going to be equal to 14 minus POH, which is 0.699. So the pH of 0.1 molars magnesium hydroxide is going to be what? It's going to be 13.3. So that is a pH of 0.1 molar magnesium hydroxide. Now, what we have to take note of is that in this particular calculation, we did not consider the hydroxide that is being generated by water. We didn't consider that. Okay. We didn't consider what is generated by water molecules. This is because the amount of OH minus that is being generated from magnesium hydroxide is so high that even when we subtract that of water from it, it still wouldn't be anything much. It won't make any big effect. So it is negligible. So what do we do in a situation where we have a concentration of OH minus to be very low? To be very low. So let's say we have concentration of a base like sodium hydroxide to be very low or even below. So let's say the concentration of this is below 1 times 10 exponent minus 7 molar. Okay, then what is going to happen when we find the pH? The pH will appear to be acidic. Okay, what that means is that when we consider 0 point, or let's say 1 times 10 exponent minus 8 molar sodium hydroxide. Now we know that sodium hydroxide will dissociate to give us OH minus concentration to be 10 exponents minus 8. In other words, it's the same as this. Okay. Now, when we find the pH of this, what are we going to find? If we find the POH here is going to be negative log of OH minus concentration. And so we'll have 10 exponents minus 8. And this will give us a POH of 8. And so pH is going to be 14 minus 8, which will be equal to 6. Wait, this is not an acid. So how do we have the pH to be below 7? That means there is something wrong. So in a situation where we have the concentration of a strong base to be very low, that means it has been so much diluted. So when it is below times 10 exponents minus 7, then in this case, we would need to consider the autoionization of water. Now, when we consider that, we know that water will dissociate by itself, and it will give us H3O plus OH minus. Okay, and this is called autoionization of water. And we said when that happens, the concentration of H3O plus and OH minus are equal, and it is usually 1 times 10 exponents minus 7. So we have an expression called Kw. So 1 times 10 exponent minus 7, and we have the same thing for OH minus 1 times 10 exponent minus 7. So in a scenario such as this, we'll have to consider this concentration of OH minus also. So if that's happened, we will now be looking at POH as negative log of the total OH minus concentration. So this time we're looking at the total. What does it mean? That means we are adding that which is produced by water and that which is produced from the diluted sodium hydroxide. So it means we'll be having negative log of that which is from water is times 10 exponent minus 8, and the one that water is giving us is 10 exponent minus 7. Okay, so when we punch this, what are we going to have for POH? POH is going to be 6.59, sorry, 6.959. So when we take this out of 14, pH will be 14 minus 6.959. And so we find out that pH is equal to 7.041, which makes sense, right? This makes sense because we should be expecting a strong base such as sodium hydroxide to have a pH that is above 7. So in a situation like this, we consider the concentration of OH minus generated from water. And just a quick reminder, remember that KW is equal to the concentration of H3O plus and that of OH minus. Okay, we said these two will have the same concentration, and that value is what 1 times 10 exponent minus 7 and 1 times 10 exponent minus 7. So to understand this further, you can go back and check our video on auto-ionization of water. So I hope this video helps you. Remember to like and subscribe for more tutorials.